Hello. Today I'm going to add some comments and corrections to a video that I made earlier this year about a heater project where I got some real data. And here you can see the results that I got. This is for a second order plus dead time. And one of the things I was wondering about was that the short time constant was very, very short. And here you can see it says T0, that's the short time constant, that's for the heater. And it says it's 0.02 minutes, but really that's just rounded up. It's about 0.15 minutes, which is less than 1 second, barely less than 1 second. And it really should have been modeled as a first order plus dead time system. So you can see that even though this is a second order system, the data that I got, let's see, we have a control output here, the green line, and it's going plus or minus 20, or it's going 20% to zero, 20% to zero, and you can see that it's kind of a PWM type of affair. And then the cyan line, or light blue, is the process value, or the temperature, and the red dotted line is the estimation from my model. And you can see that the model kind of changes in very sharp zigzags. And that's what led me to believe that really this should be modeled as a first order plus dead time, because the short time constant is so short. It's shorter than a second, it's shorter than the sample time. And, you know, because of that, it should have been modeled as a first order plus dead time. There's another reason also, and that is that this data that I got has a resolution of a quarter of degree, and the times are not even seconds or even periods. Close, but not quite. And because of that, calculating out the derivative gain would be kind of a problem. It could be a little bit noisy, but the other thing is that the derivative time constant ends up being, or the derivative gain ends up being pretty short. So, or time constant is short. So maybe it wouldn't have any much effect anyway. Now, what I want to do, and what I did, is I did a first order plus dead time model. And here you can see that's the first order plus dead time. And it's almost the same solution. Now, uh, you can see that I'm using the same data, so I have the same control output, the same recorded process value or temperature, and the model looks about the same, except for maybe a little bit of time shift due to a different dead time. And you can see the dead time here is 2.35, and here it's 2.13. But other than that, it's pretty much the same data. Now, the first order plus dead time only has one time constant, and one of the things that you should notice, it's kind of hard to tell here, and I'll get a better view later. This time constant 30 minutes, and here you can see the short time constant and the long time constant add up to close to 30 minutes. So it didn't really change the answers by all that much. So let's take a look at the data that I got. And this is a comma separated variable file. And you can see we've got the time, and you can see that the times are moving up there a little bit longer than a second. Then this is the control output. And the data that I got goes from 0 to 0.2, but it really needs to be scaled up by a factor of 100, so it's 0 to 20%. So I have to multiply all these numbers by 100. And then the heater gain, or this is the actual recorded temperature, and this changes in steps of a quarter of a degree. So here you can see all the data that was recorded. So this is the format that I like to get my data in, and I use the same data for both the first order plus second order plus dead time system. So another thing I want to look at is the the run or the data. Let's see, this is the first order plus dead time data here, and this is the second order plus dead time. And what I'm trying to do, let's go back to the image here, is I take the error between the target or the estimated and the actual, the process value and the estimated value, and I square it and I sum it for the whole graph. So there's, I think, over 5,000 different seconds. And then I have the sum of squared errors, and then I divide it by the number of readings, so I get a mean squared error. And what I'm trying to do is find these parameters here that closely match the recorded information, the actual data, so that I minimize the mean squared error down to 0. And I get pretty close, and I get about the same results with both the first order plus dead time plus the second order plus dead time. So let's go back to the two different runs. Okay, that's okay. This is the second order plus dead time, this is first order plus dead time. Now, I don't understand why the first order plus dead time takes so much longer when on other computers it goes much faster, a matter of seconds. But you can see that what starts out, this is the mean squared error. And when I first start out, then you can see that it rapidly decreases. And as I get closer and closer to the solution, the change or the gradient gets smaller and smaller and smaller. And so the improvement is smaller and smaller. And eventually I get down to less than 0.16. And you can see that this one does the same thing. It does about the same thing, and it gets down to 0.16. So they both get down to 0.159, which is just below 0.16. And you can see that the gains are roughly the same. The time constant for the first order plus dead time is a little bit over 30 minutes, and you can see that this is about 30 minutes, the sum of the two. And I'll show you how that affects the gains. And then I have the offset, which is 45 degrees, just about, and the dead times, because these are in minutes. So if I go back to the recorded data, you would see that again, the images, they are about the same. So you could use the solution for either one. It would probably be okay. So let's go back to, oops. Other things, this is the resulting controller gains. And what's different is what affects these the most is probably the gain and the closed loop time constant. And I'll show you the formula for the closed loop time constant, but I've got it so that it's automatic. I probably could have used a fixed value for the closed loop time constant, but the smaller the closed loop time constant, and there's actually two of them, the faster the response, and also the gain will be a little bit higher. Another thing to notice is that, let's go back to the images, is that the dead time is about 45 degrees, and you can see, well, you don't see the 45 degrees here. The dead time is about 45 degrees, and the reason why it's so high is that I think that there's an extra heating element in there that's constant. Because if I go back to this image, you can see that the 45 degrees, which is about here, no, 45 degrees, that's about here. Okay, that's the ambient. Well, you see the ambient, the real ambient starts at 25, and the calculated ambient is 45. So it's almost like there's another 20 degrees worth of heater So there's a constant heat source in there, and I could have added a constant heat source, but that really does the same thing as just changing the bias. So the ambient temperature really is 25 degrees, but it's almost like there's another heat source in the cabinet that is adding an extra 20%, and it's continuous. So this is the controlled change, and then that's probably why they only needed 20%, and then there's an extra 20% that we don't see. So I just wanted to explain why the ambient temperature is so high. And again, it's because there's an extra heater or some sort of heat source in the cabinet. So let's go back to the data. Another thing I want to point out is that this is the starting mean squared error, and this is for the heater, the second order plus dead time. And I have the alpha. Alpha is a learning rate. And what I have to do to minimize the sum of squared errors and the mean squared error is to use this alpha, and I calculate out a gradient, and I'll show how I calculate out the gradient, but I take the gradient and I multiply it by some small number, which is this, and that's a step where I change each one of these parameters. This is the gain, the short time constant, the long time constant, that's the offset or the bias, and that's the dead time. And so then what happens is from one iteration to the next, it's always trying to go downhill. The gradient is a positive number, but what we want to do is subtract from the mean squared error, so we have to use the negative of that value, and I'll show you that in the program, and we want to step downhill. Excuse me. And this is a 5-dimensional problem because there are 5 different parameters, but I want to explain this as if this was only a 2-dimensional problem again. I've got an example on YouTube where I have just a gain and a time constant, and so that's only 2 dimensions, and you could think of one dimension as like the gain as being north-south and the time constant being east-west, and what you're trying to do is go downhill to the valley floor, and the mean squared error represents the elevation. And what we want to do is reduce the elevation, get down to the valley floor, and hopefully there's a little creek down there, whereas that's as low as you can go. Now, what you would do is you take a step north, step south, and figure out the slope north-south-wise. Take a step east and a step west, east-west-wise, and figure out the slope, and then figure out the best combination of the slope to get you downhill. And this is, you would repeat this operation over and over and over again, and eventually you end up down at the bottom. So the problem with this data, excuse me again, is that it's kind of like a meandering river. And so what you want to do is you want to get down, and the path or it has a switchbacks, and it changes quite often. So you just can't go in one direction to get to the minimum. The steps have to be small, otherwise what happens is the system will get lost, eventually like falling off the switchback and trembling downhill, or you go the wrong direction, you get up on top of the bank so that the terrain is flat, and then you don't know what direction to go to get to the valley floor. So you got to take small steps, but if you make the steps too small, what happens is it takes forever. And what I've done is I have these steps here, and you can see that they change in the size. And the reason why I do this is because if you use a straight gradient descent, the alpha doesn't change. And sometimes the steps get to be so big that you can't move anywhere without having the mean squared error go up. It's kind of like having a truck or a Class A motorhome that's too big to maneuver in a parking lot. So people talk about local minimums, and there are local minimums, but in this case, what I noticed is that if I made the steps dynamic, in other words, change them up and down according to the requirements, then what would happen is that I'd eventually get to the global minimum. Now, there are local minimums, and I'll explain that a little bit later. But you can see that what I'm doing here is I'm taking a step, and if I make a good step, what I do is I multiply the learning rate by 2, and if I make a bad step, I multiply or divide the learning rate by 2. And you can see that it changes dynamically, and eventually what happens is I get to a point where it gets down to 10, something to the minus 10th, which is below a limit that I set. And in that case, I take a step anyway, but at least I'm not going to be stepping very far, and it will calculate out a new slope that hopefully will get me going in the right direction, which you can see that it does. And I find that this method works very, very well. It doesn't get stuck. Now, if you watch the AI videos, they talk about gradient descent and variations like Ada Delta, Atom, RMS prop, and Nestra's accelerated gradient. And then also I have another couple variations with a line search, and they just don't work very well because the step size does not change, or this alpha learning rate doesn't change. And they do change, but they use an algorithm which doesn't respond quite as fast as just being able to change the like each iteration, being able to change the gain by a factor of 4. They usually have a filter that's based on the last step size, or the filter the gradient squared, or something like that to modify the alpha, but they don't work well with this data. They work well in the examples for the professors because they choose simple terrain. If you want to just use XY type terrain, again, they use simple applications like, or functions like f of xy is equal to x plus 2 squared plus y minus 3 squared. And if you were to take a look at that, it's just a concave bowl, and all you have to do is figure out what direction you want to go into, and it's easy to go downhill to get to the minimum. It's not real data. There's no noise because you can differentiate that numerically and get perfect solutions. But this is real information, and the way that I have to calculate the gradient I'm going to talk about right now. So let's take a look at these next two. Oops. Okay, these are the two programs. And what I do is first I start out with a tolerance for the mean squared error. And then I have also a tolerance for the change. As it turns out, if the parameters don't change to 6 places, then what will happen is I'll quit also. But that's not what happened in this case. In my example here, both the first order plus dead time and the second order plus dead time got down to 0.159. So that's how they terminated. Alpha, this is beginning learning rate, and this is awfully big. And but because I divide it by 2 every time it makes a step that's too big, I can have it big to start with, and then it will automatically seek a lower value that is adaptable. And this is the step size, and the step size makes a difference. The first order plus dead time is kind of a push as to whether or not step is e to the minus 4th or e to the minus 5. Either one works, but they're both much slower with on this computer, and I'll get around to that, explaining that too. These are my enumerations for my 4 parameters here and 5 parameters here. And then the rest of this is pretty much the same. But what I'm going to do is, this is my parameter list, and I have the gain, the short time constant, the long time constant, the offset, the dead time, and then this calculates out the closed loop time constant, and this is what the user would adjust to that has effect on the gains, and that is shown here. The controller gain is the sum of the two time constants divided by the open loop gain, system gain, times the sum of the closed loop time constant and the dead time. So if the closed loop time constant is long or the dead time is long, it's going to reduce the controller gain. But the formula over here is roughly the same, except for I only have one long gain. But you got to remember that this long gain here, this T0, is about the same as this gain, I mean time constant, as this time constant, this time constant. These are time constants. Okay. Also, the integrator time constant for the first order plus dead time is just equal to the system time constant. And here it's equal to the sum of the two. And I've got another video showing how these gains are calculated, or these formulas were calculated. The first order plus dead time does not have a derivative term, so there's no calculation for that. You can see that this is the formula for the second order plus dead time for the derivative gain. I've got parameters, and they're both the same. This was a trial, but this is the actual parameters that I use on both of these. Use the same starting conditions, and this was part of the trick on when I initially got this data. Like I said, if you start here, there really aren't any local minimums, although you can get stuck because you just can't, the steps are too big. You can't maneuver around the bends in the meandering river, so to speak. But if you start with a wrong guess, you can fall into local minimums, and the solution will get stuck. And so finding out these initial parameters was kind of a trick, and I equated that to playing golf, where you're outside a green, and the green is surrounded by sand traps, which are local minimums, and the green has a small area around the hole where if you get the ball there, you'll be okay. You'll be able to make a couple more putts to get it into the hole. But if you get outside that small area, the green slopes away into the sand traps. And that's about how this application seemed to work. If I didn't get close with my guess, the system would get lost in one of those sand traps. I have to have array bounds or parameter bounds, and this wasn't really so necessary with the first order plus dead time, but the second order plus dead time required that I have a bounds for the minutes or for the short time constant. And the reason why is because the short time constant would sometimes go below zero and crash. So I had to keep it from the time constant from going below zero. And then these are the two differential equations. And you can see that they're roughly the same, except for the second order plus dead time has an extra time constant here. And these are the differential equations. And you can see they're relatively the same, except for the first order plus dead time only has a y0, whereas the second order plus dead time has a y0 and a y1, which correlates to that's the temperature, and this is the temperature rate. And again, these are the sum of the two time constants I'm dividing by. Over here, I'll only have one time constant, but got to remember, again, this time constant is roughly equal to these two time constants. U is the control output. PLC people use CV or CO. Control theory people use U. This is the plant open loop gain, and the T0 and T1 are multiplied by the rate of change. So, and over here you don't have that T0 and T1 in front of the rate. There's no rate term here. Then I return the temperature, and here I have to return the temperature and the rate of change of temperature. then I have the two functions that have to get called, and they use the ODE int, which is, I think, basically a Runge cutoff 4.5. And here I have to start with the initial temperature. So this is the first element of the temperature, and here I have the initial temperature and the temperature rate, and I call this ODE int, and return the mean square error. And that's what you see on the plot, the difference between the cyan line and the dotted red line. It's coming down here, and at this point you can see the two functions for calculating out the gradient, and all it is a loop, and for each element in the parameter array, which I can kind of think of as an element or a dimension, what I have to do is I save the value, I take a step in the positive direction, I take a step in the negative direction, and then I divide it, subtract the 2 and divide it by 2 times the step, and that gives me the slope in that dimension. And after I do that with all 4 or 5 dimensions, I end up with a gradient. So then I come over here and I got the gradient descent routine, and these are identical except for what has to be printed out, because the second order plus dead time has an extra time constant. But other than that, these things are identical. And then here I have the main routine, and the main routine has these global arrays. Again, these are from the data that I was given. I got an array of time, an array of control outputs, and an array of process values, which are temperatures. And I have the heater, or the path to the data. So I have, it's the same thing for both of these. And then I use pandas to get a data frame. I extract the different parts. I have to multiply the control output data frame or array by 100, because you have to remember the scale was 0 to 1 instead of 0 to 100%, and I need 0 to 100%. And then I also have to divide the time by 60 to convert it to minutes, because I'm using the normal ISA model. Then I have the initial parameters, which were read up from above. I start my timer, and I call the gradient descent routine up here. And one I call with the T0P2, and the other one I call with the T0P1, and that's these guys right here, oops, up here. And again, the T0 means type 0, 1 pole, and this is a type non-integrating type 1, 0 with 2 poles. So let's go back on down. I calculate out, when it's done, I calculate out the time, and I print out the results. And this is printing out the gains, or calculating out the PID gains. Again, I have to calculate the estimated values so that I can plot it. This is the again, the redded dashed line. And here I don't really need this anymore. It's for debugging, but basically I write the data out to a dictionary. It's a JSON file, and this one's second order plus dead time, and this other one over here is come down here, and I call it first order plus dead time. And then the GDX, it's normally a gradient descent, but again, because I do the multiply by 2 or divide by 2 trick, I called it GDX. And then I plot the temperatures down here, and the calls are the same, except for the there's an extra time constant. So then I have recorded the data, and on my faster computer, you can see this takes 17 seconds instead of hours. And I have no idea why there's a difference, except for my faster computer has a newer version of Python. The Python I'm using on this one is 3.11, and it's a Linux Mint Debian edition computer, and it's also a 2016 computer, so it's not that fast, which is why I'm not showing the calculations real time, because it would take forever. But basically, this is much slower, and I don't know if it's not. There's more to it than just the computer speed difference. There seems to be a difference in the libraries that are called. And then to make sure that the two are the same, what I did is this. I use a program called Meld. What Meld does is it compares the difference between them, and you can see I have a slight difference for the difference in the step that I'm taking when I'm taking a step to the north and step to the south, the positive step and the negative step to figure out what the slope happens to be. I've got an extra parameter or extra enumeration value for my longer time constant, an extra time constant here, extra time constant here, slightly different equations for the controller gains, or for calculating the computer controller gains, an extra time constant here, and then this is the difference in the differential equations and the fact that I'm returning a temperature and temperature rate as opposed to just a temperature. A difference in the name here. This one's got 2 time constants. This one's only got 1. A difference in the initial conditions again. Again, the gradient routine is the same. The gradient descent routines are the same except for what I'm outputting. And there's just one less parameter to output for the second order plus dead time. So that's why there's only a change in the print statements. None of the rest of this is different. So I know that I'm using the same algorithm for both of these. It's just a matter of the difference in the model. And then here I am reading the data using Pandas, and I'm reading it into a data frame. I extract it into the 5 arrays. Again, I got to multiply by 100 to scale it. I got to divide the time by 100 or by 60 to convert minutes to hours. And then again, this is just a difference in the between 1 pole and 2 poles. Again, 1 pole and 2 poles. Here an extra time constant. Here a different set of initial conditions. I got again temperature and temperature rate. And this just has the temperature. A different file to save away, and here I had different parameters for plotting. But you can see that the 2 routines are basically the same, and it's amazing that one takes so much longer than the other, given that they're so much the same, but the solutions are very, very similar. Now, one of the corrections that I needed to make is that over here in the differential equation, let's see if I can find that again. Here. One of the things that I did, I played around with it when I first started with this, is filtering out the data. I tried using a Savitzky-Golay filter, and that changed the mean squared error, but it didn't change the results because the estimated value that I have on the plot is already pretty much a filter anyway. And then another one is that I was using cubic splines, and I shouldn't have been using a cubic spline for smoothing out the control output. And the reason why I have to use linear interpolation is that the dead times do not go in even increments of seconds. I might need a half a second or a quarter of a second or some fraction of a second like I do in this example. So I have to interpolate in between the seconds. But I shouldn't have been using a cubic spline. I need to use just a linear interpolation, which is what I have right here. So I have the time and the control output, and then I'm interpolating using the time here. And the reason why I'm using the max here is that because I got a dead time, if I'm using times that are below or less than the dead time, if I subtract the dead time from them to pull out a data point, a control output, before the data starts, then what ends up happening is I get a control output of 0, and I didn't want that. I want to use the minimum control output, the 20% that I was starting with. So this is properly getting the control output. And again, this is the 2 derivative terms. So that's probably one of the big improvements that I made. Well, I don't know if it's a big improvement, but it is right as opposed to using the cubic spline, which was wrong. So I found out that simplifying the filtering didn't really make any difference to the solutions, and it's probably better, and this linear interpolation is definitely faster than the cubic spline interpolation. So if you have any questions, write them out in the comments. Hit a like if you find this interesting, and I'll see you in the next one. Bye.